every Friday, 8 o'clock in Beijing. We met on ICANX Talks, Connect World and the Universe. So this is one of the best time I always enjoy very much with you. Alice from Peking University. So proud met you every Friday. I'm so proud we have ICANX attract so many audience from all over the world. Every Friday is our seminar time. Every Friday is our ICANX time. We use the latest work from everyone from all over the world, the top scientists, to connect all of us. So, and this November, we have 4 speakers. The first one, Maria from Spain, already finished last Friday. And this week, we have Mark Allen from USA. So he's going to talk tonight. And next week we have Christian, was from Twitter, is from not Denmark, is from Holland, Netherlands. And then the last week of November we have Zuan Kai Wang, was from Hong Kong. So and this November 4 speakers, 4 wonderful talks. And today we have Mark Allen. My great friend. I think I know Mark more than 15 years. We met on conference. We met in many different, area, and I visited his lab about, several years ago. It's quite amazing, and he really did a lot of work. He won a lot of awards, and it also is one of the big pioneers in this field, not only, jump in first, but also deliver, something very special, like his, start up a company, long time ago for the, implantable sensors inside the body, inside the heart. So that's the first one approved by FDA. So we're so proud of that. So Mark, so today, what kind of story you going to talk with you, and all our panelists will join this. And this is Mark Allen from University of Pennsylvania and in Philadelphia. And today is going to talk about the story for MEMS. Something happened in the past, something happened now, and something will happen in the future. Is that right, Mark? Yeah,
That's right. No, I'm looking forward to that. Okay, so I will go ahead and get started then. First of all, Alice, thank you very much for this invitation and this opportunity to address people from around the world in this wonderful seminar series that you've put together. I really enjoyed watching some of the other speakers in this, and I'm honored to be able to join this group and tell you a little about my own research, microelectromechanical systems, and in particular applying them to medicine. And I'll give you some thoughts about what we might be able to do, some examples of what we've done, and maybe where we might go moving forward. Before I do that, though, I'd like to spend a minute and introduce my university. So my university is the University of Pennsylvania. It's located in Philadelphia, Pennsylvania. Which is about halfway between New York City and Washington, D.C. So we have a wonderful chance to visit both of those cities as well. It is a very old city. It's one of the places where the United States government was first formed, and a lot of the founding documents were established. And you can see on the back of some of our money is Independence Hall, which is the building where a lot of these founding documents were written, still standing. You can visit it today if you like. And we have things like our famous bell, which has a crack in it here, which happened during ringing the bell to commemorate liberty. And also one of our strange favorite foods here, which is chopped up meat and cheese all melted together. So if you ever come to visit, please give this a try. Our university is one of the older universities in the country. It was founded in 1740 by Benjamin Franklin. He's on the other side of the money, the man on the other side of the money there. And we have about 21,000 students spread across 12 schools, of which engineering is one of the schools. The group our research group is the Microsensors and Microactuators group, and our overarching theme, our overall theme is developing and using new micro and nano fabrication technologies to build things. And sometimes those things are in very different research areas, and one of them I'm going to tell you about today, the biological area. But some other themes are microfabricated electromagnetics, compact energy storage, environmentally degradable devices, and something new that we've been thinking about, which is the Internet of Things, which is enabled by nanotechnology. On the right is a picture of a portion of my group that attended recent graduation. So you can see the two young ladies in the center of that picture who got their PhD degrees in the most recent commencement. And the reason I want to highlight them is because I'm going to be talking about, in part, some of their work in my presentation. So I'll be talking about this wonderful stuff, but you should be thinking about them as having carried out this wonderful work. Okay, so jumping into the topic at hand, I think a question that we could ask is, how healthy are you? How healthy are we? So we have a kind of difficult time trying to figure that out. Obviously, if we feel sick, we can go to the doctor. The doctor can try to figure out what's wrong with us, and he has many tests available to him that he can use, which is wonderful. In the virtual world, the video game world, it's a lot easier because there is a little row of hearts here for this guy who's running around doing his adventures. And if he gets hurt by some monster or something like that, the number of hearts reduces. And so we can always kind of tell whether he is doing well or doing poorly, and we can adapt our strategy appropriately. Yet, for people, we don't have such an easy visualization to understand how healthy they are. We do have some examples, though, in the real world, and we might think about them as guideposts for how we might get to something like the picture on the right. So I have two cars that I own. The one on the left is one that I bought when I was an undergraduate student, and I still have it over these many years. Next year it will be 50 years old, which is a little scary. And it has almost no electronics inside, right? It is a triumph of mechanical engineering. Gears turn rods, and rods push valves, and valves turn things that might generate a spark. I think maybe there's one transformer in the car to make a spark. If something goes wrong with that car, it's very hard to tell what's going on. But my other car is not only a wonderful example of mechanical engineering and materials and electrical and so on, but probably the biggest difference is information. If there's something wrong with the car on the right, a mechanic can plug something into the car and tell me right away, hey, this is wrong or that is wrong. And if I think about my old car, I've actually had mechanics listen with the same instrument, the stethoscope, that people use to diagnose people. But my new car communicates with all the sensors in the car. There's manifold pressure, airflow, oil temperature, fuel level, acceleration of the car, rotation and speed, the composition of the exhaust, and on and on and on. And all of these, the outputs of all of these sensors are computer coordinated. You can access them in high or low resolution mode. What does that mean? It means that you can get all the data if you want, or if you want, you can just get, hey, something is wrong. A little light goes on saying something is wrong, go have your car checked out. And the car can use this information to optimize its operation. And it works. So if I look at the graph on the left, this is the number of reported problems per 100 of 3-year-old vehicles. So the lower that number is, the more reliable the vehicles are, and the vehicles have gotten more and more reliable over the past 20 years. On the right is one measure of performance of the car, which has to do in this case with its fuel efficiency. And you can see that while we made the cars better by using this information, we've also made the cars perform better, so more dependable and better performance, just by integrating sensors throughout the car. So the obvious question is, could I do something similar by integrating sensors throughout people? And then maybe I could get to the point where I would be able to tell how healthy someone is. So in order to do that, I'll introduce this concept of medical microsystems, or MEMS. Now, not everyone on this call is an expert of MEMS, so let me define it a little bit clearly. So medical microsystems, to me, means microsystems that are based on the use of microfabrication and nanofabrication technologies, the clean room, lithography, etching, deposition, and so on, to create mechanical structures, sensors, and actuators that can interface with parts of the body, either in vitro or in vivo, that means either in the laboratory or inside the body, to diagnose or treat disease. So that's a big definition. And you might ask, well, yes, I believe that that idea of putting sensors in the body is a good one. Why use MEMS technology? Why use micro and nanofabrication technology to do it? I think there are two major reasons. The first is that MEMS allows you to make things small. And often it's true in the body that the smaller something is, the less invasive it is, the easier it is to integrate with the body. And then the other reason is that MEMS technology allows me to do a lot in a small space. In one compact system, I can put a sensor and I can put a chip and maybe an antenna for RF communication and so on and so on. And that then allows me to create a system that can not only collect information, but transmit it to a central point. So before we jump in and start talking about implantable devices, we should ask ourselves, what could we do with wearable devices? And of course, the answer is we can do a lot, right? So this is a very old picture now, maybe 10 years old or so, of one of the first Fitbit devices. You put on your wrist and it will measure a lot of different things. And if you look inside of that device, you'll find a lot of different parts, which are shown on the right. But from the MEMS perspective, I've highlighted that part down at the bottom. There's an accelerometer, a gyroscope, and a magnetometer. So something that tells you about your motion and something that tells you about the magnetic fields surrounding you. You have 9-axis motion tracking, so it can really tell how you are walking, how you are running, whether or not you trip over something, how many steps you are climbing, and so on, all in one MEMS chip. And as I go through this talk and talk a little more about some of the implanted devices, we should keep in mind that we also have available to us these devices that could potentially communicate with the implanted devices and gain more information or even be the readout for the implanted devices. These are all physical sensors. There are people now who are thinking about using chemical sensors as wearables. So this was some work that was published by Wei Gao on sensing biomarkers in sweat. So the idea is that you have a number of chemical sensors available to you, and these chemical sensors, when they are wet, because you are exercising and sweating, can analyze things like the concentration of ions, the concentration of lactate, and so on, and tell you something about your physical condition. And I think these external sensors are very, very valuable and will be a key part of how we instrument people to diagnose disease. But there are, and they have tremendous advantages, such as there's almost no damage to the body, and anyone can install these sensors. Anyone can put a wristband on and so on. You don't need a doctor for this. But there is a role for implantable devices too. And in particular, implantable devices allow you to get more intimate interactions with the physical or chemical media of the body that are being sensed. So we have to infer things from external sensors, but with internal sensors, we can measure right there. And so we may be able to get more information or more accurate information. We also have the possibility of interfacing with inaccessible measurands. What does that mean? Well, in the example of the sweat sensor, I can sense the chemical composition of the sweat. But what if I want to sense the chemical composition or the oxygen concentration, say, deep within a muscle? That's harder to do unless I'm actually inside the muscle doing that measurement. So immediately when people think about implantable sensors, they think, oh, I have to go to the doctor and he's going to cut me open and put sensors inside. That's not necessarily true. So we could think about sensors, for example, that we could swallow. I'll show you some examples in a moment. We could think about sensors that are put on the skin, pierce the skin to access the body, but the needles are small, so maybe it doesn't hurt so much. And then we can also think about delivering permanent implants by using catheters instead of surgery. And these sorts of devices are a very nice compromise between getting deep within the body and not causing a lot of trauma to the body. And I'll show you some examples of all of these. So maybe the most obvious thing that we could think about first in putting MEMS into the body is to put sensors in the gastrointestinal tract. So this is work of two different companies. I'm not involved with these companies. It's just very interesting work for two different applications. So in the application on the left, to understand medicine compliance, there's a very interesting problem, especially with older patients. They have to take many pills and they're older and maybe they forget. And so they don't comply, they don't obey the doctor's instructions. So this company, Proteus Biomedical, had the idea of what if we were to put a small sensor on each pill that would be able to tell the physician when the pill was taken. And then the physician would know, yes, you've taken your medicine, or no, you haven't taken your medicine. And if that becomes a problem, then the physician could have additional care, for example, prescribed to you. Another example by given imaging is to improve colonoscopies. So when you get to a certain age, the doctors like to look around your insides of your gastrointestinal tract to make sure there is no cancer, especially in the colon. And this is a painful and invasive procedure that's usually done under anesthetic. So this company, Given Imaging, made the idea of putting a little camera inside of a pill. You swallow the pill, it takes pictures as it goes all the way through and comes out the other end. And then the doctors can analyze the pictures to see if there is anything going on. So avoiding that problem. We can also think about doing things in the mouth. So this is some work of a colleague of mine. I was not involved in this work, but I thought it was very interesting, where someone who has been paralyzed, apparently, even if your spinal column is injured high up, you still retain some ability to move your face, and in particular, your tongue. And so there's the possibility of putting a magnet in your tongue, right there. Some people do it just for jewelry, just for cosmetic reasons. But here you could imagine putting a magnet in your tongue and moving it around your mouth, having magnetic sensors either implanted in your teeth or external, and using those to control a wheelchair or control a computer and really allow people to have access again, when they are paralyzed and communicate with the outside world. So very interesting things we can do that are still minimally invasive. So hopefully I've convinced you that implanted devices don't necessarily need to be invasive. Let me now switch and tell you about some devices and products that we've built in our own lab for understanding and treating disease. So let me start first with transdermal sensing. So I think we're all familiar with the concept of a transdermal patch. It means through the skin. If I would like to access bodily fluids, what's inside of us, in a minimally invasive way, I could use this concept together with a small array of needles, say, that would pierce the outermost layers of skin and allow us to access the body. I could then place sensors on the tips of these needles, and using those sensors, I could monitor, say, proteins of interest that are flowing in the body. And using MEMS, we can make the needles small, and we can make the sensors even smaller. And so perhaps the pain associated with the needle piercing the skin would be greatly reduced. So this microneedle area is one that I've been working on for a little while, mostly from the fabrication technology perspective. But lately we've been thinking about putting sensors on the tips of these. And let me show you one of the projects that we've done recently, which is looking at monitoring of cytokines. So cytokines, if you're a physician, you know that these are intracellular messages that regulate important functions in the body. So these are messages exchanged by cells, usually through the secretion of proteins that say, I'm doing okay, or I have a problem, please help me, among other things. And so monitoring the profiles of these cytokines can be very important, especially in the early diagnosis of disease. Often the cells are saying, I need help, before the rest of the body gets so sick that you notice it and go on to the doctor. And as one example, there's a particular type of cytokine, IL-8, that has been shown that when it is increased over a long period of time, it's correlated with the presence of early cancer. So what if we could use these transdermal microneedle sensors to sense cytokine profiles in the body in real time? So that was sort of the motivation for this project. And I'll show you how this is done. So basically, first let me focus in and show you how the sensor itself works, and then I'll show you back and off and show you the entire device. So the way this device operates is that I have an array of microwells, and these microwells, if I look in the side view in section B here, have two layers of gold that are separated by a very thin layer of insulating material. And what I'm going to do is I'm going to decorate the gold surface and the edge of the gold electrodes with an antibody that is specifically binding to the particular cytokine of interest. Then I'm going to monitor the impedance between these two electrodes as a function of time. And if that cytokine binds to the antibody, we will see that as a change in the impedance of the microwell. So you might ask, why MEMS? Why should I use MEMS for this? And of course, the answer is twofold. We want to make it small, but it turns out that MEMS can also improve the sensitivity of a device like this. If I focus in very close to the edge here and look at the electric field that's generated between the upper electrode, which is here, and the lower electrode, which is here, you can see that this electric field really only penetrates a very small distance around the edge. Another way I could look at it is the figure on the left, where I have these wells, but the effective sensing region is really only the perimeter of the wells. And the penetration depth is on the order of the thickness of the oxide or the aluminum oxide that separates the two electrodes. So a large number of small wells should improve my sensitivity over like one big well. And so another rationale for looking at MEMS. So we can fabricate these sort of devices using typical microfabrication technology. We typically use a glass substrate, deposit and pattern our multi-layers of gold, alumina, and gold. And then we will pattern the microwell array in the overlapping region between the two electrodes, open up connecting pads, and then when we're finished, we'll use laser micromachining to dice out individual microneedles that have the sensing region at the tip. So very straightforward MEMS fabrication. And here's sort of a sequence of how this is done. So all the way on the left, we use glass wafers for this, fused silica wafers. You can see wafer scale view of the devices. If I zoom in on one of the devices, you can see the bottom gold and the top gold and the overlapping area with the microwells. And if I zoom in on the microwells, you can see the microwells that typically consist of 25 individual wells that are 2 microns in diameter on the sensing region. Then I can individualize these using, instead of dicing, I'll use laser micromachining so I can get a needle shape with the sensor at the tip. And the typical width of these needles is about 900 microns or so, and the length is about 4 millimeters, to give you an idea of the size. So that's how we make them, but how do we test them? Do they work? So let me show you how we demonstrated that these devices can indeed sense cytokines. So working with collaborators, we obtained 2 cohorts of mice. One set of mice were normal mice. So they just exhibited their normal mouse cytokines, and we use them as a control group. Transgenic mice were also obtained, and these were mice who've been genetically modified to express human IL-8 cytokine. So different mice will have expressed different amounts of this cytokine naturally. So what we did was we took these mice, we immobilized them. We did a transdermal insertion of the needle, either into the thigh muscle or the tail vein of the mouse. We measured the impedance change in real time. Then we took serum from the mouse and we sent it to the laboratory and had the serum measured according to the gold standard of current cytokine measurement, which is called ELISA. And then we compared the two to see how well they did. And here's a picture of the mouse. I'm sorry, the immobilization is done with some tape. Mouse is sleeping, so it's okay. Here's the needle that's inserted into the mouse, and you can see that the packaging and interfacing is much, much larger than the actual device that winds up getting inserted. And on the right, you can see the correlation between the sensor readout for different levels of cytokine expression correlated with the cytokine expression as measured by the gold standard on the x-axis. And we have a very good correlation indicating that now we no longer have to send these samples out to the lab to be measured. Instead, we could do it in real time in a doctor's office, or maybe even chronically over time for somebody who needs that longer time frame to get a time series profile of cytokines. The mice that did not express human IL-8 did not have any reading change and did not have any ELISA signal, and so that was good. That showed that the negative controls were working. If you'd like to learn more about this work, we just published it in Microsystems and Nanoengineering. I encourage you to take a look at that. So that's an example of transdermal sensing, but could we imagine extending this idea to fully implanted devices, things that are fully inside of the body? We would have the possibility of a more accurate and predictive sensing of our disease states. We have more physiological parameters to measure. But if I'm going to do that, I need to figure out how these devices will exist inside the body for long periods of time and how we can get information out. For example, if we're going to use radio frequency communication, how do we get information out from the lossy medium of the body? Well, this idea is not a new one. People have been thinking about this for quite some time. Here's an early example of this. On the left, you can see 3 small sensors on someone's fingertip. This work that I'm going to describe to you was published in the IEEE Transactions on Biomedical Engineering in 1967. That's quite amazing, right? It's even older than my old car that I showed you earlier. The way this device worked is that there was a cavity. If I look down here at figure 2, there's a cavity, and this cavity was bounded by a flexible membrane on either side. So as the pressure changed, cavity was squeezed slightly closer together or further apart. The walls of this cavity, the top and bottom of this cavity, were bearing these inductor coils. And the inductor coils, together with the parasitic capacitance between them, formed an LC resonant circuit that could be read out by an external magnetic loop. So it's powered by external inductive coupling. It's no internal electronics, it's small. It was demonstrated in the eye of rabbits as a glaucoma sensor, a sensor to look for excessive pressure in the eye. But it had a problem. It has several problems. It worked. It was fantastic. It worked. But it was not stable to operate over long periods of time. And it had a very short communication distance. It was necessary to put the antenna directly very close to the eye. But of course, that was many years ago. Could we do better today? And what I hope to convince you of is yes, and now is the time to do it. And the reason for that is for what I call the technology convergence. So 3 things have come together to make these wireless implantable microsystems a reality within our grasp now. The first is MEMS fabrication technology. So we have new materials for MEMS. We have a whole manufacturing infrastructure to build small things. We can do better than what was done in 1967. The second thing is that we now have low power circuitry. So if I can manage to get a milliwatt of power into the body, I can do a lot with it. So I can start to think about energy harvesters or advanced batteries that allow me to store energy that would power circuitry for a long period of time. And then finally, we have wireless electronics technology. So we can communicate over longer distances, we can sense smaller signals, and once we get those signals out of the body, we also have the internet. So as soon as the signal comes out of the body, it can be in the doctor's office as fast as the internet can carry it. So putting these things together, now is a great time to be working on these problems. So let me illustrate this by an example that we did a few years ago. Started off in our lab as an experiment to make pressure sensors for jet turbine engines, and ultimately wound up being a sensor that could be used within the body to monitor patients that have congestive heart failure. So we've had a tremendous medical success over the past 20, 30, 40 years. And that is that coronary deaths from, say, a heart attack are reducing every year over time. The rate of them is reducing every year over time. And the reason for that is we have much better medical care. So in 1980 or 1990, a heart attack might cause you to die. Now we have therapies and interventions that will allow people who have suffered a heart attack to continue to survive, which is fantastic. But there is a problem, and that problem is that now these people are living with a damaged heart. So heart failure has almost tripled. So heart failure is your heart is weak, it's not strong enough to pump blood the way it used to, and so your activities are limited. Maybe you have some pain in your heart or chest and so on. So we've turned this acute disease into a chronic disease. And that's really good because otherwise these people would be dead. But now we have to manage the chronic disease. So how could we manage chronic heart disease? Well, we might be able to get some inspiration from thinking about the way diabetes is managed. So if I look on the left-hand side of this slide, diabetes has something that can be sensed, in this case, the level of blood glucose. I have a sensor for it, which is a prick your finger and put blood on a test strip. There are now some interesting, more advanced ways to do it that are implantable as well. And then I have a treatment, which is I can inject insulin into the body and keep the blood sugar under control. So I have this feedback loop, something I can measure, a way to measure it, and a treatment. So if I think about heart failure, we know that we can measure the intracardiac pressure, the pressure inside or near the heart. And if we do that, we have medicines that, or the doctors have medicines that can be used to keep that pressure under control. But what we don't have is a sensor. Right now, or previously, the only way that could be done is in the hospital using something called a catheterization, where the doctors would take a long tube, thread it up through your body into your heart. There's a pressure sensor on the tip of the tube and measure the pressure. And that works fine. But of course, you can only do it at that one point in time. You can't walk around with a catheter inside you, or maybe you shouldn't. So we were thinking about, could we do something about this? And thinking about the sensor that we saw for the eye implantation, where we have a cavity that's bounded top and bottom by two flexible, in this case, plates, mechanical plates, with an inductor and a capacitor arranged in parallels, forming a series resonant circuit and allowing us then to interrogate this resonance with an external magnetic loop. The differences, though, are we're going to use MEMS technology to build this, and we're going to take advantage of the improvements in electronics and communication to communicate with it inside the body. So the way that we fabricate this device is fairly straightforward. Instead of using a silicon wafer, we use a silica wafer, etch a recess in the silica wafer, form electroplated coils within that recess to form the inductor coil, take two of these structures, flip one upside down, fusion bond them together and dice them. The fusion bond leads to a hermetic seal at the edges, which gives us great stability and allows us then to implant this device for long periods of time. So here's a picture of what one of these devices looks like next to a small US coin. Here shown that device at the bottom left on the tip of a catheter. So what the doctors can do, as shown on the right, is that they make a little incision in the artery in your leg and they thread this catheter, very common procedure. They thread this catheter up through the body, through the heart, and into the pulmonary artery. So that's the artery that runs between the heart and the lung. Once the sensor is in place, they pull a little wire, the sensor detaches from the catheter, and they pull the catheter out and leave the sensor embedded in a branch of the pulmonary artery. Then with an external antenna, it's possible to read out the pressure in that area very close to the heart. So what that looks like is something like this. In the upper right, you can see sort of the real-time data. It looks like traditional heartbeat data. The pressures are lower, right, because this is the right side of the heart, not the left side. So the units here are millimeters of mercury or torr. And you can see that we can replicate the pressure wave in very high detail, including the dichrotic notch. And you can see what looks like a little wave as this goes up and down a little bit. So that's the patient breathing in and breathing out. So we can even detect respiration. And now, since this device is implanted, we can take a reading of the systolic pressure, which is the top pressure here, the diastolic pressure, which is the bottom pressure, and the mean pressure, and that's what these three lines are here, as a function of time over many months. So how do the doctors use this device? So this is a very complicated picture, and I'm not going to explain it all, but I think qualitatively we can gain a lot of information from looking at it. So this is a plot of pressure as measured by the device as a function of time. It's about a year on the x-axis. And again, there's the three pressures, the maximum, the minimum, and the average. That's what those three lines are on the graph. The gray bar down here is what the pressures should be, what the doctors think the pressures should be. Each one of these green boxes up at the top is the doctors changing the medication of the patient, trying to drive the pressure into the gray box. So there's a couple of things to see here. One is the day after the patient leaves the hospital, the pressures are too high. So even after they got the patient stabilized in the hospital, the next day, things had changed. Without the sensor, there would be no way of knowing that. But with the sensor, the doctors can start to adjust the medication, drive the pressures into the region where they should be. And you can't see this, but most of the boxes on the right are the doctors lowering the medication to try to find the minimum value that keeps the pressures within the stable range. How well does it work? Well, we did a clinical trial of 550 patients. The way this clinical trial was done is that all 550 patients received the sensor, but only half of the patients were treated according to the data from the sensor. Only half of the patients received constant monitoring and adjustments of blood pressure medication to keep the pressure constant. The other half were treated according to the normal method of treating patients that had congestive heart failure. And what was looked at was how often these patients had to go to the hospital. They were very sick, right? How often they had to go to the hospital because of a heart problem. So the results of the trial are summarized in this graph on the left. On the y-axis are the number of hospitalizations. And on the x-axis is time. And this is about almost 2.5 years of data, something like that, on the x-axis. So you can see a couple of things. First of all, for the first 3 months or so, there's very little difference between those who were treated without using the sensor, which is the blue line, and those who were treated by using the data from the sensor, which is the red line. And that's kind of interesting because if I look back to the raw data, it takes about 3 months for the doctors to figure out what the medication should be. For each individual person, it's a little different, before the pressures are driven into the band where they should be. Once that happens, though, we see a steady and diverging increase in, or difference in the number of hospitalizations between the treatment arm using the sensor and not using the sensor, until finally, out at 12 to 15 months, there's almost a 40% reduction in hospitalization because of having the sensor. All the doctor needed was more information that we were able to supply. And so this device ultimately was approved by the FDA. It's available. Hopefully we will never need it, but if we do, it is there for us. And this may be the beginning of permanently implanted MEMS devices to help us understand how healthy we are. So let me show you just one more quick example of this. And this is a figure from two colleagues of mine, Professors Van der Spiegel and Lucas, and Dr. Andrew Richardson, thinking about an implanted brain-machine interface for restoring tactile sensation. So there are many patients who, for whatever reason, have lost the ability to feel things in their hands. Sometimes it's because of diabetes, for example, that causes nerves to atrophy in the extremities, so fingertips, toes, and so on. And sometimes it could be because of injury or other reasons. So would it be possible to try to restore the feeling of sensation for these patients so that they could feel things again? Not necessarily feeling the finest of fine feelings, but to be able to do things like grasp a coffee cup or pick up an egg and know how much pressure they are applying so that they don't break it or it doesn't slip out of their hands, things like that. So we have some interesting things at our disposal we can look at to do this. So we could imagine, for example, building MEMS sensors that could be implanted in fingertips that would allow us to sense the normal and shear force associated with grasping an object. Those sensors could transmit information to some sort of external device like a watch, which could act as a collocation point, which could then either have within it computation or transmit information to a more powerful computer that could then send sensory stimulation signals to a peripheral or a cortical neural interface to shock the nerves either further up in the arm, which are still healthy, or maybe even all the way into the brain, so that people would be able to gain a feeling that is associated with tactile sensation. So that's the idea of this, and obviously a very ambitious project that we have been thinking about and started to work on now for a couple of years. The first step perhaps being building the tactile sensor. So we've been thinking about ways to do this, and obviously one way to do it would be to use a wearable device, right? We could imagine having a glove that we could put on the hand, and the glove would have the tactile sensors in the fingertip, and that would transmit information. The challenge with many of these patients, however, is that they have lost a lot of mobility, and it's not easy for them to put on these gloves and to be able to change things in and out. So we were thinking, could we imagine building tactile sensors, perhaps based on similar technology to the heart sensor, but now incorporating, instead of being passive, incorporating electronics and circuitry and transmit information so that we could compress and send out this tactile information. And the answer is yes, we can build these types of sensors. So here's an example. Again, building these devices out of fused silica. Here's an example of a device down here. I've got this upper fused silica plate, which will form the mechanical plate that will do my deflecting or twisting, depending on if normal force or shear force is applied. I have, instead of one capacitor electrode, I have multiple capacitive electrodes that allow me to tell which part of the diaphragm is deflecting. These electrodes then go to feed-throughs, which allow me to feed this capacitor information through to a circuit. Since this is a sensing technology and also a packaging technology wrapped up together, I could think about putting the circuitry within the same package. So in cross-section, here's the view, side view of, say, the capacitor plate. So here's bottom capacitor plate here and here. This upper capacitor plate is floating, and so it varies the coupling between these two lower capacitor plates and therefore changes the capacitance depending on the pressure. On the other side of this fused silica plate, I have a custom application-specific integrated circuit that can take this capacitance readout, that can process it, turn it into a pressure, and transmit that pressure to an external reader. And then I have a coil that's also been formed on the fused silica substrate. The coil allows me to do two things. One is it allows me to scavenge energy from the wrist device that then is used to power the circuit. And it also transmits the information, the pressure information of interest to the wrist device. These are all built up using multiple layers of fused silica that are patterned, and then the chip is attached and then stacked, fusion bonded, and laser cut. Here's a picture from one side of what one of these looks like. The glass is transparent, so you can see through it. You can see the insides. And here is one of these devices sitting on the fingertip of the student who fabricated the device. And the devices work just fine. So on the right-hand side, you can see the capacitance measured by the capacitor as a function of, for example, in this case, normal force. This is the wireless readout of the capacitance, so as measured by the wrist device. And you can see that depending on whether the capacitor, this is in vitro data, whether or not the capacitor is just pressed on directly by the mechanical compression device, or whether it has a layer of silicone between it to simulate skin. We can get different pressure responses. That's okay, because these devices can be calibrated once they're implanted. And you can see that we have done some in vivo experiments where we do similar loading experiments with a cadaver monkey hand, and we can get the same response and transmission of data from the cadaver hand. So I think this will be a tremendous opportunity to think about additional implantation opportunities throughout the body, and there are many more that we can think of. These are all physical sensors. Chemical sensors will be a little more difficult, but certainly they will be coming permanently implantable. We already have transdermal chemical sensors like the cytokine sensors that I showed you. And now people are working on permanently implantable glucose sensors, for example. Very tough problem to get chemical sensors to have very long-term stability, but I'm confident that, that this will be coming in the future. So let me spend the last few minutes of my talk thinking a little bit about some future directions, where some of this might be going. So what are some things that we might think about working on? So I'm a MEMS person. I like to work on MEMS problems, and there are a number of interesting MEMS problems within this technology convergence that's happening right now. The first one are the fabrication challenges to shrink the device size even further and improve device delivery even further. So MEMS can make very small things, but by the time you get done building the MEMS structure and packaging it and making it biocompatible and on and on and on, these things start to get big. So we have to start to think about tricks like co-forming the MEMS structure and the package itself, kind of like maybe what these tactile sensors are trying to do, although they're still big. I think a game changer will be when these devices get small enough that you can inject them through a needle, so-called percutaneous injection, implant them directly under the skin with relative ease. A second challenge that we might think about is communicating with these smaller and smaller devices within the lossy medium of the body. So the body is not very good at allowing RF signals through, right? We are all made of conducting fluid, and this conducting fluid damps these RF signals. How can we do it if we keep making things smaller? There are some people looking at other methods of communication, such as ultrasound. Could we use ultrasound to communicate with devices in the body, much like submarines do in the lossy medium of the ocean? That's kind of interesting. A challenge there is that there are many acoustic interfaces within the body. You have soft tissue, you have bone, you have air in the gastrointestinal tract and the lungs and so on, which would reflect these acoustic waves. So we have to think about that. Or maybe there are some other techniques that we might be able to work on. Low power circuitry, we can keep pushing the definition of low. Try to make circuits that instead of operating on milliwatts, operate on microwatts or even fractions of a microwatt. If it's hard to get energy in and out, let's do more with less. Co-locating this functionality, one of the key advantages of MEMS, will be something that we definitely will want to work on. Instead of injecting 5 different sensors, maybe we want to inject one sensor that does 5 different things. And then finally, even though this is not a MEMS challenge, I think it's a very important one that we need to consider, and that is data synthesis and machine learning algorithms for actionable interventions. So one of my favorite examples of this is the Google map that shows you where the traffic is on the road. And they use the information from people's mobile phones to do this. Now, a mobile phone has to be the world's worst traffic sensor, right? There is nothing in a mobile phone that senses traffic. And yet by collocating and taking all of this information and processing it, we can get an amazingly accurate picture of what the traffic is like. And I think there will be a lot of this type of thinking to be brought to bear once all this information does make it out of the body because of our implantable MEMS sensors. Another future direction that we could think about is, instead of making things out of traditional MEMS, we might think about making them using MEMS techniques with other materials. So for a couple of examples that we've worked on in our own lab are neural electrode interfaces, how to interface with nerves or cortical tissue. It's a big problem because the body does a good job walling off these devices that are implanted in the brain or the spine or in the peripheral nerves. And the reason is because they're not tissue. Well, what if we were to make the devices out of tissue? What if we were to make them out of collagen, for example? We have some tantalizing data that suggests that these sorts of devices are better tolerated in the body than conventional MEMS. Another potential example is a lot of what I've talked about now has been chronic. I want to monitor the heart pressure of someone with heart failure for the rest of their life, 10, 20 years. What if I have a different disease state where I only want to measure what's going on for a week, a day? Perhaps I could think about building MEMS out of biodegradable devices that could then do their job, transmit their information, and then dissolve away, much like the doctors that use things to sew up a wound, so-called sutures. Once the body heals, they dissolve away as well. So we could start to think about these as additional future directions. But however we do it, whether we tackle these key MEMS challenges that I mentioned on the previous slide, or some of these interesting new directions, I'm hopeful that we will wind up with the instrumenting the body concept becoming more commonplace as time goes on. So if I summarize this talk, I would say that the information that's extracted from the body through these distributed embedded sensors can guide medical treatment, maybe even optimize people's performance. You can get a better workout, you can exercise more healthily, you can do a lot if you have information. MEMS will be a key enabler of this concept, whether it be wearable, transdermal, catheter implanted, or what have you. We have many alternatives. And we have approval. We have FDA approval for these devices for permanent implantation. More are coming, right? So I showed you one of the early devices. More is coming, more are coming. And I think the reason this is happening is because of the technology convergence that I mentioned. We know how to build these MEMS structures. We know how to build them out of biocompatible materials. We know how to make low power circuitry. We know how to take advantage of wireless electronics and measurement of very small signals. So now is really an exciting time to do this. So before I end, I really have to acknowledge a lot of people because, of course, this was a lot of work that was done, and I wish to make sure that my colleagues who really did most of the work are acknowledged. So for the cytokine sensors, this work was led by Dr. Naijin Song, one of the two ladies that I showed you in the very beginning of the presentation, along with collaborators at Rutgers University in New Jersey and University of Pennsylvania Medical School. The CardioMEMS device, the heart sensor, is done by people at CardioMEMS Inc. And I'd like to particularly acknowledge my former students, Michael Fonseca, Jinwoo Park, and Florent Cross in this. And then finally, the fingertip implantable device, Dr. Lin Du, is the other young lady that you saw in the beginning, led this MEMS work together with Han Hao and professors from Penn Engineering and the Penn Medical School. And of course, none of this can be done without money, so I have to acknowledge multiple funding sources, including DARPA and NIH for funding this work. So with that, I'll say thank you. I appreciate, again, the opportunity to speak with this group, and I look forward to our panel discussion and maybe thinking more about some of these ideas. Thank you again.
Okay, thank you, Mark. Very nice talk, as always. Actually, we have plenty of time to talk at the panel discussion. before we go to the panel discussion, I have a question. It's from Qi from Xi'an. He's want to know, the power level for the implantable sensors. So the power level, like milliwatts or something. Yeah. Can you comment on that?
Yeah, so that's a great question, and for the passive devices, it's a little bit hard to say, right? Because these devices are really re-radiating captured energy. And so these signals that we receive back from these devices are maybe minus 100 dBm. So that's picowatt level. But the active devices are running at much higher power levels because they require energy to run the integrated circuits and so on. And so these are more in the tens to hundreds of microwatt level.
Okay, thank you very much. Yeah, now we can move to the panel discussion. Let me first introduce our panelists. Today we have Xinyu Liu from University of Toronto and Canada. Professor Liu was actually an expert in this area. He done a lot of work for the microwells and related work for this biomedicine. So welcome, Professor Liu. And we have another professor as from Zhejiang University, UIUC campus, was a new international campus. Hu Huan, Dr. Hu Huan was graduate from UIUC and then back to China, joined this international campus and done very nice work, also related with the biomedicine. So welcome, Professor Hu. We have our challengers here today is Dr. Quan San Yang. Dr. Yang now is in MIT as a postdoc, but he graduated from Professor John Rogers Group and Northwestern. I think just years ago. It's pretty fresh. Now I should have a lot of questions for this. And yeah, let's welcome everyone. Please, Chen San, you ready?
Yes. Yeah. Many thanks for your talk, Professor Allen. So I learned a lot. So for my first question, I would like to ask, for example, in traditional MEMS, we usually use silicon because silicon has a very good mechanical properties, such as the insignificant hysteresis, something like that. So I would wonder, what do you think about the opportunities of traditional silicon-based MEMS in the biomedical applications or the implantable applications?
I think that's a very insightful question and one that we should discuss. When I teach my beginning graduate level nanotechnology course, I talk about fabrication technology being divided up into the technology of silicon and the technology of everything else all put together. And silicon is the biggest piece, right, by far. So why didn't we use silicon in these devices? There were really two reasons. One is that the RF transparency of silicon was not as good as that of fused silica. So it would have been a little harder if we had a completely silicon encapsulated device to be able to get energy in and out of the device. There would have been a little bit of loss associated with the silicon. The second is that the silicon material, figuring out exactly the details of its full biocompatibility is still ongoing. And so clearly there are fantastic examples where I think this is happening, such as some of the cortical implants that we see from Michigan and from Utah and other places. But at the time this work was being done, that was still being worked out. However, there's nothing that prevents us from borrowing the silicon technologies, and I think that's really a key piece. So thank you, silicon people, for developing all these wonderful technologies. We're going to try to use them for silicon and for other things as well, other materials. I
see, yeah, many thanks. And my second question is that for the LCR sensors, like the cardio maps, it actually has for example, the capacitor as a sensing component and also the inductor. So all this kind of things actually are very sensitive to the surrounding environment, right? Not only the pressure, but also the temperature, like something like that. So how could you, for example, like remain the stability of this kind of LCR sensor in Vivo?
Yeah, it's also a wonderful question, and obviously one that we spent a lot of time thinking about during that development of that device. The temperature is not so much of an issue, luckily, in this application because of the sensor's location within the core of the body. So there's only a very small variation of maybe a degree or two if you are very sick or not, things like that. But the bigger problem is the body reacting with the sensor and growing a layer of tissue over top of the sensor that could change its mechanical response. And we thought about trying to fixing this problem. Our approach was really two ways. One is that in traditional endovascular applications, say putting in a stent, right? The doctor will thread a catheter in, there will be a balloon on the end of the catheter, and the balloon will blow up and open the blood vessel. That's very traumatic for the blood vessel, right? It causes a lot of damage. It's damage you need, right? But it's still damage. And the body reacts by growing a lot of tissue there. So we did not do that in the implantation of our sensor. It goes into basically healthy arterial tissue. And so as a result, the body does not do as much to reject the sensor, but it does react. It does react. And so there the key is that if you imagine the device having a layer of deflecting mechanical plate, so it's not a membrane, it's actually a mechanical plate. And then on top of that, whatever the body is growing, the mechanical plate has to remain the most stiff part of that stack of material so that the tissue is a negligible perturbation on it. So that's fine, you can make that plate very stiff, but then what about the sensitivity? Because now it doesn't move very much, right? So then you have to combat that problem by making the gap, the capacitor gap, very small so that very small motions of the plate still give you a larger capacitance change. So you are absolutely right. Thinking about all the different methods, all the different drift characteristics associated with these sensors, when they're going to be implanted for 5 years, 10 years, it's critical for their success.
Yeah, thank you very much. And also my last question is for the chemical sensors. Actually, for the physical sensors, we like this kind of sensors, they don't require direct contact to the surrounding environment. So we can use some well-developed waterproof material as the encapsulation or packaging materials. But for chemical sensors, like we need them like to contact directly to the surrounding environment. Like, what do you think about like, is there like, what's the main challenge on the packaging strategies of this kind of chemical sensors, and how could we improve the lifetime or stability of this kind of chemical sensors?
Yes, I think you've pointed out one of the parts of this work that, or parts of this field that needs still tremendous work. And I can restate your question by saying we have chronic implanted physical sensors, like the CardioMEMS device. We have short-term or acute chemical sensors, like the Cytokine device I showed you, or a glucose microneedle, or there are several examples of this. Why don't we have chronic chemical sensor implants? There's a tremendous need, right? Tremendous need for this. Every diabetic in the world would love to have something like this. And it's because of two things. One is exactly what you said, that it's hard to make a hermetically sealed chemical sensor, right? Because if you can't communicate chemically with the body, it's a bit of a challenge. The other is that the chemical sensing media tend to not be stable. So in the case of the pressure sensor, the sensing medium is a deflecting fused silica plate, which, with maybe the possible exception of a deflecting silicon plate, as you mentioned before, is one of the most stable materials around. In the case of a chemical sensor, often we have antibodies or enzymes or some other very complex chemical that gets degraded with time. And so we have to think about how to fix that. So I've seen a couple of strategies that people use. One is imagine that you have, instead of one sensor, you have 10 chemical sensors. 9 of them are sealed and 1 of them is open. And then when this one stops working, you unseal the next one and unseal the next one. So there have been companies working on this unsealing technology. I think there's a company called Microchips that was using this for drug delivery, for example. The other, which is more far out and maybe not in the realm of the engineers, but if it could work, would be wonderful. Could we convince the body or trick the body into regenerating the enzymes on our MEMS device in the same way that it does for its own tissues? Now, I don't know how to do that. I throw that out as a challenge to the biochemists among us. But if we could do that, we could provide the sensing platform and the body could provide the sensitive chemicals. But that's going to be very tough.
It is. Actually, I must think about, chemical sensors, especially gas sensors now, it's still a big problem. So it is very necessary, but it is really hard. And thank you, Chen-san. Yeah, my challenger this time very good. So, okay. Yeah, Hu Huan, did you have questions?
My turn. Yes, I also have 3 questions. Can you hear me?
Yes.
Yeah. Hi, Mark. Thanks so much for inspiring talk. My first question is about your cardio MEMS. We all know how tough it is to get FDA approval. So I can imagine there must be numerous challenges you have faced during this commercialization process. Could you share with us some of the key or crucial challenges you have faced in this process?
Sure. I know we only have a short time, so I could have a very long list of challenges. But I think the biggest challenge for us maybe is not as much of a challenge now, which was we walked into the FDA basically saying, here is this strange new technology, MEMS technology. We would like to put it in your heart, please. And that was a tall ask, right? And so maybe the only worst thing would be put it in your brain instead of your heart. And so what we did was we started off with a different application by putting sensors in aortic aneurysms in the belly. The same sensor, the same materials, the same readout mechanisms, and so on, and showed that that was safe and effective. And I think that helped give the FDA a lot of comfort associated with doing this. The other thing is that once FDA approval is required or is achieved, that's only half of the battle. The other half is who will pay for your treatment. And so one of the challenges that the US healthcare is facing, at least, is that we have these technological solutions and they're becoming very, very expensive. So if we can make a story like, yes, it will cost money to implant this device, but the healthcare system will save money because people stay out of the hospital, that becomes a more compelling argument for adopting new technology from a financial perspective.
Thank you. My second question is, I watched your interview yesterday. So you mentioned that MEMS technology now is the right time to do commercialization. As you know, in China has built many, I think almost more than 10 MEMS foundries across China, and many fresh PhD graduates, some postdocs, and junior faculty like me. We're all looking forward to join this commercialization of MEMS. As a successful entrepreneur, Would you please share with us some of the advices or some pitfalls that a new entrepreneur might face, and we can learn from those lessons?
So I will, thank you. I will give you maybe a small thoughts, but the most important thing to do is to look at a very recent talk by our friend and colleague, Kurt Peterson. So Kurt, as you know, is the father of MEMS commercialization, small companies, and so on. And I just attended a talk of his, which was very inspiring about how to do all of this. And it should be posted on YouTube, I believe, shortly, and also downloadable from the NSF National Nanotechnology Coordinated Infrastructure site. But from my perspective, I would say that if it's possible to engage, if you have an idea, first of all, not every idea is one you should start a small company around, right? Some are better licensed to larger companies that have lots of infrastructure. But if you have an idea, especially in the bio space, it's a different set of economics than what many people are used to in the MEMS field. So in the MEMS field, we're used to making millions of devices, right? In the bio space, and each one costs a tiny amount. In the bio space, we make a smaller number of devices and each one costs more. And sometimes finding a foundry that's willing to engage you on that level can be a bit of a challenge. They want to keep their foundry full with hundreds of wafers a week, and maybe 100 wafers would satisfy the entire yearly demand of a biomedical device, something like that. So finding a foundry that's willing to work with you to do that. The second thing I would say is that ideas are, we all have great, as academics, we all have great ideas. We think they're great ideas anyway, but that's not enough, right? What's really needed is the execution on those great ideas. And sometimes it's true that the people who execute and the people who dream up the ideas are different people, right? And so putting together the team that can really help you get your ideas through is very important. In the United States, at least, what I've heard is that investors tend to invest in the team as much as the idea as a result. I don't know if that is as helpful, but I definitely encourage listening to the master, Dr. Peterson, and he can give us much guidance here.
Yes, thank you very much. I watched one of his talk given University of Michigan by Kurt Peterson. Yeah, that's very helpful. Okay, my last question will be from my own personal interest as a junior faculty. How do you balance the tough tenure life and also if you want to do entrepreneur, how to do the balancing? Both are pretty tough. How did you survive and get successful in both of those?
So that you are absolutely right, and I will give you some advice. It might be old-fashioned advice. I'm not sure, so I have to think about it a little bit. But my advice has always been to junior faculty: first, grow your scientific career, your scientific networks, your reputation. Establish that. Then do the entrepreneurial activities. I think that the reputation and the scientific achievements and the people that you meet at conferences, as we have met, across the panel over time, are really valuable, because when people are trying to decide, should I invest in your idea? Should I do this? They're going to call up other people that they know. What do you think? Do you know this person? And it takes a little time to build that up. So my advice would be, first, as an assistant professor, focus on your tenure, your career, your academic job, and then expand. But it might be old-fashioned advice, because I'm seeing more and more enthusiastic, younger and younger entrepreneurs try to do everything. And I'm not going to tell them they're wrong, because the excitement is just amazing.
Okay, thank you very much.
Okay, Mark, maybe I adding some words here. I think your advice is not, some old-fashioned advice. Actually, it's very reasonable. I think not only in US or in China is the same thing. For the young generation, once you choose a job to be a faculty member, first you need to, set up your reputation in the academic field. Because you remember that you share one articles was 1967. So what the paper doing? It's doing exactly the wireless sensors, right? So the people's, in the academic area need long time, right? So especially you will eventually come out some ideas that really takes time. I think for the young faculty, the same thing. Sometimes you think it's quite easier, but not that easier, right? It's always need you pay attention, pay a lot of, time and to a lot of efforts to solve the maybe the same or the important problem, and then eventually you can get something. I think don't be too rush. Yeah. Okay. I copy and follow your words. Okay, Xinyu.
Sure. Thanks, Mark, for the fantastic and also very inspiring talk. And it's always fascinating to see these successful stories to translate our academic results into a real product. So actually, some of my questions have been asked by Professor Hu and also Guanshan, Guanshan. So just maybe another follow-up question is, about the manufacturing challenges you have seen or you have go through about this cardiac MEMS device. Should we assume as long as we can find a collaborator, we'll be able to translate our lab prototype into a real product? And any challenges in terms of manufacturing or quality control you have seen the company has went through?
Yeah, so I think there are several questions or issues along those lines. With a very broad brush, you could say, well, there would be two different types of MEMS products that you might want to commercialize. One where the novelty and intellectual property is in the design, but the fabrication uses well-established techniques. Those are probably the easiest ones to get into a foundry. That doesn't mean they're the easiest to commercialize, but they're the easiest to get into a foundry. The foundries understand them and so on. The second kind is where the innovation is in the fabrication technology itself. Those are much harder because the foundries don't know this technology. Maybe you don't want to teach them the technology because then they may be able to use it. Usually the foundries say, well, if you teach us something, you need to be free to use it for others, which is not an unreasonable position because they don't know who the next customer will be. And sometimes what I've seen companies do is they will use foundries for parts of the process, and then they will bring the parts back and do the proprietary fabrication within their own companies. That costs much more money because now you need to have some sort of fabrication line. But where that works is if the process steps are not super small CMOS, highly demanding lithography type of processes. So for example, in the cardio-MEMS case, the sensor fusion bonding, which was how do you do fusion bonding in such a way that you melt the glass together, but keep the circuits inside from getting too hot. That was a processing innovation that the company kept in-house for a long time before transferring it to a foundry.
I see. Thank you. Another question is about the chemical sensor, because I'm also working on like a diagnostic biosensors. Very often we kind of design this device in a one-time use disposable way, but you also talk about if we really put into the implantable situation, the packaging is an issue. Also in the biochemistry area, people has been looking at reusable biosensor designs, including the ones for protein sensing. Any thought on that? Will that be useful for this implantable devices?
I think so. We could imagine devices that we could rejuvenate, say. So in other words, suppose we implanted and I'm completely making this up, so it may not be reasonable. But suppose I implanted a glucose sensor in my arm, and the glucose sensor only worked for a week before it started to drift. Maybe what I could do is to inject either into the sensor or near the sensor some material that would refresh the sensor, maybe some glucose oxidase that could adhere to the sensor again and have it work for another few weeks. So something like that might be very interesting. I think another area thinking about these biodegradable devices is, suppose you could make the device small enough that you could inject it through a conventional syringe. So you could inject a device, have it operate for a week, it stops working, it dissolves away, and you inject another device. Yes, you have to inject yourself once a week, but maybe that's better than pricking your finger 3 times a day, something like that. So I think there may be room for all of these types of innovations while we figure out how to make these chemical sensors last for a long time in the body.
All right, thank you, Mark. So Alice, I think I will just hold the time, and then I think it's almost 8:30.
Okay, very good. Yeah, Mark. Yeah, very nice panel discussion, and thank you everyone. Very important questions. I think we got almost covered the MEMS, chemical physics and the bio and all these things, and especially a lot of people now is really interested, for put the academic result into the market. Hu Huan says that, we have in last 10 years, maybe in all over China, we have many MEMS foundries was, set up. So that's a good news. That's also a good opportunity for the people to follow Mark, right? Mark got his company by product get the FDA, approved. I hope we can have some Chinese company, can get CFDA, approved. Hu Huan, you're on the way. Yeah, we hope. Okay. Yeah, very nice. Mark, thank you very much. I think we panel discussion is okay. Yeah. Now my time to deliver a certification to you. So Mark, yeah, I'm so proud that I have you on the stage to tell MEMS story in the medicines, opportunity, examples, and perspective. So thank you very much. That's the certification. I will send the e-version to you. I hope next time I met you, then I give you, this real copy. Thank you very much.
Thank you. And thanks again for the opportunity.
Okay, thanks. Yeah, so today we have a special thing is for Xinyu. Xinyu, are you there? Yeah.
Yes.
So,
yes.
Xinyu, yeah, please introduce your conference. Yeah, we hope
Sure.
everyone know that.
Sure. Thank you, Alice, for the opportunity. This is a real nice time for us to promote our conference next year. MARS is the international conference on manipulation, automation, and robotics at small scales. It has become a flagship forum for cross-discipline research in the areas of microrobotics and automation. So the conference has been, we have 4 times in the past, and it stably attracts 300 to 400 attendees worldwide every year, and from these different areas and disciplines such as robotics, materials, chemistry, and medicine. So it is a real nice opportunity for everyone to connect with communities and with especially colleagues from different disciplines, and also exchange ideas and scientific expertise. And also we have seen many new collaboration opportunities fostered or enabled by this exchange opportunity. So the next year, the MARS conference will be held at the University of Toronto campus in July 2022. So at the moment, the committee aim to set up the conference mainly for in-person attendance. We hope after 2 years of break because of pandemic, we could see many colleagues and friends who has been looking forward to reconnect in person through this conference. Of course, we understand the people who cannot attend this conference because of those travel restrictions. We accept video presentations, but that need to be submitted in advance. So next page, Alice, please. So yeah, so the conference mainly, so the topics we want to cover here is mainly micro nano robotics and their applications, and also technologies for manipulation, characterization, and automation at those small scales, and also related to Mark's talk. And then we have seen many researchers presenting at the conference on MEMS and NAMS, and also those applications. So the conference accept full papers, also short papers. And also we are flexible on this. We also accept a one-page presentation only abstracts. And in addition, we also encourage our folks to organize special sections. And usually those sections will include 5 or 6 invited talks. I think this is a nice opportunity to gather colleagues working on the same area or same topic to exchange ideas. So the conference will be held in the downtown campus of University of Toronto. So besides this academic events, you could have time to enjoy the dynamic Toronto city. And also you can visit many attractions nearby, such as the Niagara Falls, which is around 1.5 hours drive from the city. So with that, we hope we could see many of you next July, and look forward to many colleagues attending this conference. Thank you.
Okay, thank you, Xinyu. We're glad to see mass conference eventually come out. We're waiting for 2 years. Actually, I got invited to give a plenary talk. I think it's 3 years ago. Now, yeah, I'm still dreaming come to Toronto next July. Yes, let's have this worse. Elon Musk go to the mass, right? We go to the mass in Toronto. Yeah, next year. Yeah. Okay. Yeah. Very nice. Yeah. Thank you. I hope can get more people coming through and can get more people go together. We can host some special issues. Yeah. Okay.
Sure.
Thank you, Xinyu. See you.
Thank you. Thank you, Alice.
Yeah. So yeah, next week, yeah, we come to get some advertisement. Next week is very special. We not only to have IKX talks and Friday morning we also have another special issue. As because next Friday we will have these lectures of Wu Wangyi. It's very famous, mechanical biology. The field, the founders, and the lectures will be given by Professor Larry. He's the winner of this year's Wu Wangyi Award. So he's going to deliver a talk for the mechanical biologies from cell to molecular in the vascular biologies. So see you next Friday in the morning. And in the evening, we have IKX talks is continue. Yeah, we will have Christian was from University of Twente and Netherlands. We'll have a very nice team, for the panelists and the moderator is Martin, and we'll have Julia as ex-challengers. We will see Xinyu again, and also Xinyu is best friends, Zhi Hongnie in Fudan University. So next Friday, we see you twice in the morning and in the evening. Okay, that's all for today. Thank you very much.